Recording already? Now we are.
Yes. So welcome back to the second day of the Algebraic graph theory and content information workshop. And I'm the chair. I'm Sam, and I will be hosting for the morning section. So it's my honor to have David Roberson from Technical University of Denmark to do the first speak. So David, it's all yours.
All right, great. All right, well, first of all, thanks for inviting me to give a talk. It's nice to have these workshops and conferences like this, even when we can't necessarily travel. So this talk is really about, the heart of the talk is about a notion of homomorphism indistinguishability, which I'll define in a few slides, but basically you say that your two graphs are homomorphism indistinguishable over some class. They have the same number of homomorphisms from every graph in that class. And the point of this talk is to sort of try to understand these types of relations on graphs by looking at a construction that essentially takes a connected graph G and constructs two graphs G0 and G1 in a way that we're able to sort of pretty carefully analyze when a graph will have a different number of homomorphisms to this G0 and G1. And of course, this condition will have something to do with the graph G. So that's basically the idea of the talk. So now let's get into the details. So, okay, first you need to know what a graph homomorphism is. Probably many of you already know, but if you don't, it's just a function from the vertex set of one graph to another that preserves adjacency. So it maps edges to edges. So here I'm using this tilde to know that the two vertices are adjacent. So here's an example of a homomorphism from the 7 cycle to the 5 cycle, right? So I essentially am taking this path of length 3 in the 7 cycle and kind of folding it up into just a single edge over here. Okay. Now, whenever you have a homomorphism from one graph to another, you can look at sort of the pre-images of each vertex. So, I mean, for instance, the pre-image of this vertex would be these two vertices over here. And similarly, this vertex would be these two vertices. For this vertex, it just be this single vertex. Okay. And what you see is that, well, first of all, if we don't allow loops, then all of these pre-images, they're independent sets. Okay, because a vertex is not adjacent to itself. So that means that you can't map two adjacent things to the same vertex. And the second thing is that, okay, if I look at two different pre-images, say this one and this one, right, you can have edges between these two because they correspond to two vertices that are adjacent. Okay. Whereas if I look at, say, this one and this one, I can't have any edges between these two because there's no edges. There's no edge between these two vertices over here. Okay. So anytime I have a homomorphism, I get this partition into these pre-images, and this partition has these properties about where the edges are allowed. So it's just sometimes helpful to think of a homomorphism in that way. Okay, and of course, another popular example of homomorphism are colorings, right? So if I take a proper coloring, so I assign assign colors to my vertices so that adjacent vertices get different colors. And then this is the same thing. Let's say I use K colors. This is the same thing as a homomorphism to a complete graph on K vertices, right? So I just think of the vertices of the complete graph as the colors. Okay, and for this talk, we're going to be counting homomorphisms. And so I'm going to use this notation hom of f comma g with a little h to denote the number of homomorphisms from f to g. And then if I have a big H, I denote just the set of the homomorphisms, right? So this is just the cardinality of this set. Okay, now it turns out that I guess about 50 years or so ago, Lovász showed that by counting homomorphisms, you can sort of recover the notion of isomorphism. So what he proved is that two graphs are isomorphic. Of course, this just means that they're the same after relabeling the vertices, right? So I can obtain one graph from the other by just relabeling the vertices. So their two graphs are isomorphic if and only if they have the same number of homomorphisms from any graph. So for any graph F, the number of homomorphisms to both G and to H is the same. Of course, if this is true, then this is true because the number of homomorphisms doesn't depend on the labeling of the vertices. But the other direction also holds. So it's a non-trivial result, but it's not sort of a very, very difficult result. Okay, and then the question arises, or maybe it doesn't arise, depending on what types of questions you like. Well, what if we, instead of counting homomorphisms from all graphs to the two graphs, we restrict to some family, okay? And this leads us to the notion of homomorphism indistinguishability. So this term, I think, was coined by Martin Grohe and some other authors. I forget the other ones at the moment, in a paper, just a paper a few years ago, but I think the idea has been around. And in particular for a family F of graphs, I would just call it F indistinguishability, or say that the graphs are F indistinguishable. They would say they're homomorphism indistinguishable over the class F, but that's too many syllables for me. And I'll use this notation, which is just like this isomorphism symbol, but with the subscript, the F from that, which is the family. And it just means that the number of homomorphisms to the two graphs from any given graph in the family is the same. Okay. And in fact, you probably know some relations that can be defined this way, other than isomorphism, of course. That's the first one we already saw. But then, of course, it's an algebraic graph theory conference, so we all know what cospectrality is, probably, meaning that the adjacency matrices have the same eigenvalues. And this is the same thing as having the same number of homomorphisms from cycles. You might have heard this result phrased as, it means that the two graphs have the same number of closed walls of any length. That's the same thing. If we include both cycles and paths, then you get that they're cospectral with cospectral complements. If you do trees, you get this notion of fractional isomorphism, which is like a linear relaxation of isomorphism. And then this is by Dvorak and independently Delgo and Rattan, and both of those sets of authors also generalize this to looking at the class of graphs with tree width at most k. And it turns out this is equivalent to another notion that's already been studied. It means that the graphs are indistinguishable by this k-dimensional Weisweiler-Lehmann algorithm. This is some kind of partitioning algorithm on the graphs that can sometimes distinguish them. More recently, Martin Grohe also looked at tree depth at most k and gave some characterization in terms of first order logic. There are a few, I guess, not 2 years ago, me and Laura Menchinska showed that if you look at the class of planar graphs, you get something which is called quantum isomorphism, which is a notion we defined using a certain type of game that you can win classically if and only if the graphs are isomorphic. And then if you also allow the players to have some sort of like quantum strategy, then you get the notion of quantum isomorphism. And it turns out that this is equivalent to the graphs being indistinguishable with the class of planar graphs. Dvorak also showed that there are some proper subfamilies of graphs, in particular the two degenerate graphs. So these are graphs where every induced subgraph has a vertex degree 2 or less. And this is actually already equivalent to isomorphism. Now, I think some questions are natural to ask here. So, like, maybe you could ask, well, what families does, for families F, does this relation already coincide with isomorphism? Right? Obviously, all graphs, and Dvorak showed also two degenerate graphs. But another question that has been asked is, for instance, what if we consider graphs of some bounded degree, say graphs of maximum degree at most 3 or maximum degree at most k for some k. The other thing is, like sort of under what conditions on the classes F and F prime should these give, say, distinct relations? Like, are there some types of classes of graphs that always give rise to distinct relations? So what you might notice from this list is not all of them, but a lot of them are minor closed families. Okay, so the exceptions would be the two degenerate graphs, which correspond to isomorphism. So they somehow aren't distinct from this family of all graphs. And the other exception is okay, technically cycles and paths is not closed under minors, but if you take disjoint unions of cycles and paths, and also disjoint unions of trees, these are minor closed. And it doesn't change the relation to close under disjoint union. But cycles are not minor closed, even if you close it under disjoint union. And so that's a bit of an exception, but this is also the only relation here that is not closed under taking complements. So maybe sort of restricting to minor closed families is somehow natural. Maybe not, maybe it's a red herring. Someone told me that recently. But I think it's natural, at least, to ask, okay, well, maybe there's something special going on with minor closed classes. And if you disagree, then well, you can stop listening to this talk if you like. But, I think it's an interesting question. That's what we're going to focus on, although we're also going to talk about these classes of bounded degree. So as I mentioned, somehow this closing the family under disjoint unions doesn't change anything. And that's because if I take the disjoint union of two graphs, right, and this number of homomorphisms, it's just a product of the number. So I can already determine this number from these two numbers. Right? So this doesn't change the relation. Okay. And the real question that I'm interested in, that I really like to know the answer to, is if I have two families, F and F prime, that are distinct and they're closed under minors and also disjoint unions, then are these two relations necessarily distinct? Okay. And I don't know, I think it's certainly, to me, it's very interesting, and I don't really see why it should or shouldn't be true, but I don't have an answer either way. But the work in the talk that I'll present is sort of an effort in that direction, although it doesn't answer the question. Now, this question is, the question two, it seems a bit more concrete, but actually it's equivalent to question one. So given some connected graph G, right, is it possible to always find two graphs, G0 and G1, such that, well, first of all, G has a different number of homomorphisms to the two graphs. And also, any graph that has a different number of homomorphisms to it, this implies that actually G is a minor of that graph F. Okay. So this condition here, this is equivalent to saying that G0 and G1 are F indistinguishable, where F is the family of graphs that don't have G as a minor. Okay, this is just by definition. Okay. Yeah. And so what we want to do is we want to come up with some, hopefully find some construction of some G0, G1 that would fit this criteria. Okay. So what we actually are gonna do is, okay, so like I said, these questions are actually equivalent. This is a small exercise that you can do for homework if you like. It's not very hard, but maybe not obvious from the first look. So what we're going to do in this talk, we're not going to answer those questions. What we're going to do is we're going to take a connected graph G, and we're going to construct two graphs G0 and G1. They will satisfy this condition here, so that the number of homomorphisms from G to G0 and G1 are different. Okay, we can, in a certain sense, characterize when a graph F has a different number of homomorphisms to the two graphs. Okay, so I've left this very vague here because the actual condition is somewhat complicated to state, but we'll get to it at the end of the talk. So I haven't really said anything yet, right? This is trivial basically, if I don't define what this means. But actually, whatever this something ends up being, it allows me to prove the following corollary. So it is something that appears to be non-trivial. So it allows me to show that actually, if you consider this family of graphs of some bounded degree, then the relation you get is it doesn't coincide with isolation. So I think this to me was already somewhat of a surprise, because at first guess, I would have said that, okay, even for say graphs of degree at most 3, I would think that you would get isomorphism, just because graphs of degree at most 3 is somehow already a quite rich family of graphs. And it seems like you should be able to do some sort of like manipulations where you can somehow construct the homomorphism numbers from any graph by making some sort of bigger max degree 3 graphs. But that turns out not to be the case. Okay. And again, the point of doing all this is just to somehow better understand these homomorphism indistinguishability relations, right? Somehow we just have that, essentially we just have that table that I showed you before. There may be a few newer ones now, of examples of these homomorphism indistinguishability relations. But a lot of those are just within the past few years, and so it seems like maybe it's possible to make some more progress and or prove some more general type theorems about this notion of homomorphism indistinguishability. Okay, so let's go ahead with the construction, right? So how are we going to do it? And the construction is sort of like I think it's a pretty nice construction. So what you do is, so this is just some notation. I'll use this E of V to denote the set of edges that are incident to the vertex V. Okay. So we take some graph G, right? And then we take some subset of its vertex set, U. And we're going to define a graph G sub U. Okay. And the vertices of this graph, there are these ordered pairs. Okay. The first thing in the ordered pair is just a vertex from the graph G we started with. And the second thing in the ordered pair is a subset of the edges incident to that vertex. Okay. And we restrict we want only the ones of a given parity. So we want the ones with parity 1 if V was in this subset U. So we want the odd parity subsets. So we want the odd parity, the odd parity subsets if V were in our subset U, and we want the even parity subsets here if V was not in our subset U. Okay. So those are the vertices, right? And then the adjacency condition, okay? 2 such ordered pairs are adjacent if, first of all, the first coordinates are adjacent, okay, in the graph G. And secondly, you want that essentially the second coordinates agree on the edge UV, right? So this triangle is symmetric difference. So this says that the edge UV is not in the symmetric difference of S and T, which just means that it's either in both S and T or it's in neither S and T, right? So I think of this as S and T agree on whether or not they contain the edge UV, right? So, everyone understand this adjacency condition? Okay. So we just look at the first coordinates, check that they're adjacent, right? Okay, and then we check that either both S and T contain the edge between the first coordinates or neither S and T contain the edge between the first coordinates. Okay. Okay. And now it turns out that this graph G sub U, after isomorphism, it doesn't depend on the subset U. It only depends on the parity of the size of the subset U. Okay. So you get that, in fact, these things are isomorphic if and only if this U and U prime have the same parity. And so our G0, we're just going to let this G sub empty set. And then G1, we take to be sort of one of the G sub singletons, where if we want to actually specify one of the elements in the isomorphism class, we would pick some vertex of G and just consider this. Okay, but up to isomorphism, there's just one of these. Okay. All right, so this is our construction. And what we want to do is we want to consider counting homomorphisms from, well, okay, let's do some examples first. Okay. Right, okay, so this is the question, right? We want to find out sort of like, what are the graphs F that have a different number of homomorphisms to G0 and G1? Okay. So we're going to sort of, essentially what we're going to do is sort of try to analyze how would we count this number for both of the graphs, right? And it turns out you can somehow relate this to some lunar system, and you were going to use that to sort of analyze when you would have inequality. Okay, but first let's look at some examples. Okay, so let's look at a very simple example where we just have K2. Okay, I'll go ahead and draw this up. Okay. So here we have K2, so our graph, it looks like this, right? So let's say we have 0 and 1, right? So then what does G0 look like? Okay, well, I need a vertex. Okay, so I need to pick, first of all, I will have a vertex where the first coordinate is 0, right? And then the second coordinate is going to be some even subset of edges incident to 0. Well, there's only one edge. Let's call this edge E, right? There's only one edge incident to 0, so the only even subset is the empty set. And the same thing for 1. I will have a 1 comma empty set. Right? And now, are these two vertices adjacent? Well, the first coordinates 0 and 1, they're adjacent in my graph, right? And also the second coordinate, they agree on the edges. They agree on the edge between 0 and 1 because it's not in either of them. Okay, so that means that these are adjacent. Right, and those are the only vertices, so that's the whole graph, just K2, right? Now for, let's say I take G and I pick my vertex 1, right? So again, for the vertex whose first coordinate is 0, I will only get empty set as the only possible second coordinate, right? Okay, but now for 1, I want to take the odd subsets of edges incident to my vertex 1. Right? Of course, there's just one edge, so I just get the 1. So I get the set containing that edge. Okay, and now if I look, right? Well, the edge E, it's not in this subset, but it is in this subset. So these don't agree, right? So then there's going to be no edge between these two. Okay, so this graph is just the empty graph on two vertices. Two vertices, no edges, and G0 is just K2 again. Right? Okay, so that's a very simple example. Right? And one thing you'll notice is that, okay, K2, the graph G, which is K2, it does have a homomorphism to this, right? But it doesn't have a homomorphism to this because there are no edges. Okay, here's a more complicated.
There is a question from the chat.
Yes.
So it says, is this G sub U in the scheme of your Hell graphs?
Okay, no, I mean, it is somewhat, it does seem somewhat related, right? Because you have the first coordinate, which is a singleton, and the second coordinate, which is a subset. But it's not exactly the same. It's not exactly the same thing. So it's a little bit different, but it does have a lot of the same flavor to it. It's not the same. Yeah. Okay, so here's a slightly more complicated example. So now we just have this K13, right? So a single vertex with degree 3, and then the other vertices it just leaves, right? And then I try to draw these G0 and G1 so that these are the vertices that correspond to the middle vertex here, right? And then the other vertices, so like this vertex corresponds to this one, and so on. Right? So all of these vertices have first coordinate equal to this vertex, and similarly over here. Okay. So that's what I mean. You maybe it just takes a while to like actually write down all the vertices and figure out what the edges are, of course. But if you take my word for it that these are the two graphs, what you'll notice is that these are a well-known example of graphs that are cospectral and also have cospectral complements. Okay, so this is a 6. I've drawn it differently, of course, but this is a 6 cycle with plus an isolated vertex, right? And then this is essentially K13 with every edge subdivided at once. Okay? So these graphs are cospectral, and also their complements are cospectral. which means if we think back to that table, that they have the same number of homomorphisms from any path or cycle. Right? That means they have the same number of homomorphisms from any graph of maximum degree at most 2, which are exactly the graphs that that don't have this as a minor. Right? Okay, so that's interesting, right? Here's another example, even more complicated. If you look at the graph K4 and you construct G0 and G1, what you get are these two strongly regular graphs, the Rook graph and the Shikanda graph, right? And these are strongly regular graphs. Oh, what are the parameters, right? It's 16 and then 6 and then I want to say 2, 2, right? Okay, so these are two strongly regular graphs with the same parameters. And one thing that this means is that they're not distinguishable by this two-dimensional Weisfeiler-Lehmann algorithm. And again, going back to that table, that means that they're homomorphism indistinguishable for the class of graphs of tree width at most 2. The class of graphs of tree width at most 2 are exactly the graphs that don't have K4 as a minor. So any graph that has a different number of homomorphisms to G0 and G1 here must have K4 as a minor. Okay, so again, it's sort of interesting that happens. Okay.
So another question.
Yeah.
Do G1 and G0 have the same number of homomorphisms to G?
To G? I don't even know. They have a different number from G. But I don't know about 2G. I haven't considered that. That's a good question. Okay. Right. Okay. So those are just some examples. Some interesting things happening there. So now I want to think about counting homomorphisms to these two graphs, G0 and G1. Okay, and to do that, I'll need this particular homomorphism that goes from each of these G sub i's to G, right? So all this homomorphism does is it takes the first coordinate, it just maps the vertex, which is an ordered pair, remember, to its first coordinate. Okay, so it's simple enough. Okay, and this is always going to be a homomorphism because remember, one of the conditions for adjacency in the G sub i's was that the first coordinates need to be adjacent, right? So if I had some like U, T, right? And these two were adjacent, right? That would mean that U and V must be adjacent, right? So then after I apply this homomorphism, I will still get adjacent vertices. So this really is a homomorphism. Okay, so now what we're going to do is we're going to pick, we want to count homomorphisms from some graph F to G0 and G1. Okay, but what we first do is we take a homomorphism from F to G. We pick some homomorphism psi. Okay, and we're going to find this subset of the homomorphisms from F to G sub I. Okay. As the following. So it's the homomorphisms from F to G sub I, such that if I first apply the homomorphism to F to G sub I, and then apply this homomorphism from G sub I to G, I end up with psi. Okay. Okay. What this means basically is that this mapped psi that we've picked, okay, it's telling us what the first coordinate of the image of every vertex of F is under phi. Okay, that's all we're doing. Well, basically, we're partitioning all of the homomorphisms from F to G sub I, so according to what are the sort of if I just looked at what the first coordinates of all the images were. Okay. Okay. So given some psi, the only choice I have left is what's going to be this second coordinate. Okay. So I've sort of already pre-established what my first coordinate is going to be for some homomorphism from F to G sub I, right? But I still have left to choose what's going to be that second coordinate, that subset of edges, okay? Okay. And this gives me a partition of all of the homomorphisms from F to G sub I. And what we're going to do is we're going to try to understand how to count the elements here. Okay. Okay, and it turns out that counting these things corresponds to the solutions of some linear system. Okay, and I'm just going to I'll give sort of the idea. I don't want to go into too much detail. The point is that you can do it with a linear system, right? You don't need to really understand sort of what that linear system is, right? But we fix some homomorphisms from F to G, right? So we fix this choice of first coordinates for all of our vertices in F. Okay, we have that fixed. So the first coordinates of any homomorphism that we're going to count right now are fixed. And we need to pick some specific G sub 1, right? So we want to pick some vertex, right? Just to be concrete. So I'm going to do this for G sub 1 first, and then I'll tell you how it works for G sub 0. It's very simple, right? So basically, for every vertex of F, okay, and every edge incident to this image psi of A. Remember, this psi is a homomorphism from F to G, so this psi of A is a vertex of G. Okay. So this edge is going to be an edge of G. Okay, so for every vertex of F and for every edge in this set of edges incident to this, I'm going to have a variable. And essentially what this variable is going to correspond to is it's one, being one, it corresponds to taking, sort of choosing for my second coordinate of phi of A, I want to include the edge E. Okay, and it's 0 if for the second coordinate of phi of A, I don't want to include the edge E. Okay, so that's the correspondence between the variables in this linear system to how we construct the corresponding homomorphism. Okay. And there's just two types of constraints. Okay, the first constraint, all it's saying is that somehow sort of the choice of the second coordinate is valid, right? So remember, we needed that in some cases, the second coordinate had odd parity. In some cases, it had even parity, right? So all this condition is doing is ensuring that that's the case. Basically, if the first coordinate was V star, we need that subset had odd parity, okay? And so we want that this equation should be equal to 1, right? And if it's not V star, then our subset needed to have even parity. So we need this sum to be equal to 0. And then the second condition, it just ensures that adjacency is preserved. And basically, this equals 0. This is the same thing as saying that these two, this is all over Z2, I should have said, I suppose. So this is all over Z2. This just means that these two variables are equal, okay, over Z2, right? And that means that somehow these second coordinates the second coordinates will agree on the edge between the first coordinates. And that's all it's saying. Like I said, you don't need to understand the details of this linear system. What you need to understand is that there is a linear system whose solutions are in correspondence to the homomorphisms here. Okay? And this is for G1, but what about G0? G0 is exactly the same. Well, the only difference is that you never get this case here. Okay. So for G0, you get a homogeneous system, right? All the right-hand sides are 0. Okay. So that means that there's always a solution. Okay? There's always the 0 solution. Okay. So to be more formal, okay, this set is in bijection with the solutions to some linear system. Okay. So you have some coefficient matrix, which would depend on that psi. And then you have some constant vector, which depends on psi and also whether or not you're considering G0 or G1. Okay, and in particular, for G0, this vector is just 0, but for G1, it's not 0. Okay, so that's all you really need to know. And as a corollary of this, like I said, you always have a solution for the G0 case because it's homogeneous, right? You always have a solution to a homogeneous system. Okay, so I get that this is always greater than 0. The other thing is that there's only 2 possible values for the size of this set, right? Because they're the solutions to this linear system, right? But there's either no solution, okay, or the number of solutions is just the same as the number of homogeneous solutions, right? It's just going to be some coset, essentially, right? So it's either 0 or the same as for G0. That's the only possibility. Okay? And it would depend on psi, of course. Okay. And so what you get is that, okay, that means that for G0, you always have at least as many homomorphisms, right? Okay, because for any particular psi, this is always either 0, which is less than this, or equal to this, okay? So if I count all of the homomorphisms, I always get at least as many for G0, and I'll get strict inequality if and only if there's some psi where I get 0 here. Okay. All right. Right. And that's the same thing as saying that there's some psi such that this has no solution. So that's what we want to understand. When does this have no solution? Okay. Okay, but there's this nice thing called the Fredholm Alternative. I guess it's basically like an easier version of the Farkas lemma or something, which says that this system mx equals b, it doesn't have a solution if and only if this system does have a solution. Okay. So, and now we can sort of, since we want to know when some system doesn't have a solution, we can convert it using this lemma to some system does have a solution, right? And now we can use the solution to this other system as a certificate of the other thing not having a solution. Right? And then we can interpret that certificate combinatorially. Sort of, that's the idea. Okay, so this is just repeating what was on the last slide, right? So this happens, like this should be little h, I guess, if and only if you can find some psi such that this has no solution, which is, of course, the same as saying that these are not equal if and only if there's some psi such that this has a solution. Okay. Right, and now we're going to understand what does it mean for this to have a solution, and that's going to somehow give us our certificate. Okay, and the sort of the thing that comes out of interpreting this solution, this system combinatorially, is this notion of an odd couple for a graph. Okay, it's sort of a strange definition. It's better to just look at the picture, I think. Okay, so take G to be some connected graph. Okay, H is any graph. And we have some homomorphism psi from H to G, okay? Then we're gonna say that a vertex in H is odd if this set is odd for all something. Okay, so what does that mean? Don't try to read it, okay? Just let me explain it with the picture, right? So down here I have G and I have an H, all right? And I've drawn, so this is just a 5-cycle, of course. And I've drawn this H so that the pre-image, like the position of the pre-images sort of lines up, right? So this is the pre-image of this vertex, right? So I've labeled this vertex 0, and this is the pre-image of 0 under some homomorphism I've picked. Okay, so if I look at this vertex, right? This vertex is in the pre-image of this vertex, right? So it can only possibly have neighbors in the pre-images of this vertex and this vertex, right? Because it's a homomorphism. I can't have any neighbors in the pre-image of this thing, right? Okay, so you can look, this has one neighbor over here, right? And it also has one neighbor over here. In particular, it has an odd number of neighbors in both places, right? And so in that case, I would say that this vertex is odd. What I mean by that is that any pre-image in which it can have a neighbor, it has an odd number of them. And similarly, this vertex, you'll see, it has an even number of neighbors over here, and it has 0, which is also an even number of neighbors over here. So I would call this vertex an even vertex. And not every vertex has to be even or odd, because I could have a vertex, say here, that has an odd number of vertices, neighbors over here and an even number of neighbors over here. Right? And that would not be neither even nor odd. So that's what I mean by even or odd vertices. And of course, it depends on the homomorphism. All right. So we denote by V1 the set of odd vertices, and by V0 the set of even vertices in my graph H. Okay. And then we say that this ordered pair H and the homomorphism psi is an odd couple for G if every vertex is either even or odd, right? So that's already a non-trivial condition. But we also want that every pre-image has an odd number of odd vertices. Okay. So this is, we don't care about the number of even vertices. Okay. So you can see in this example, the red vertices are all odd and the blue vertices are all even. And there's one red vertex in every pre-image. So this is an odd couple for the 5 cycle. Okay. All right.
And David, so 5 minutes.
Yeah. Okay. So that's what an odd couple is, right? A bit of a long definition, but hopefully from the picture, it's not too difficult to understand. Right? One thing to point out is that if I have an odd vertex, right, it has to have at least one neighbor in all the pre-images where it can have a neighbor, right? It has to have an odd number, which means it has to be at least one. Right? And that in particular, it means that it has degree at least whatever the degree of the vertex is in the pre-image of, right? So here, this vertex has degree 2. So this is an odd vertex in its pre-image. It has to have degree at least 2. Okay. So then the theorem that you get by sort of analyzing this linear system stuff is that if I take some connected graph G, then a graph F has a different number of homomorphisms to G0 and G1 if and only if there's some homomorphism from F to G and some subgraph H of F, okay, such that H and the restriction of psi to H is an odd couple for G. All right. So there might be some other vertices and edges in F, right? And those vertices and edges, they still have to correspond. I mean, they still have to obey some sort of rules. They have to still allow this psi to be a homomorphism, right? But they don't have an effect on whether this is not a couple, right? So you just need to pick some subgraph H, and you need that the restriction to that is an odd couple for G, okay? Right. So I basically said this in the last slide. If you have an odd couple for G, okay, then that means that the maximum degree of this graph H is at least the maximum degree of the graph G, right? Okay, and that means that if I have a graph F that has a different number of homomorphisms to G0 and G1, okay, then by the above theorem, it must have some H, which is an odd couple, as a subgraph. And so the max degree of F has to be at least the max degree of G. Okay, and what that tells us is that if I take F to be the family of graphs with maximum degree at least D, okay, then and I take G to be this K1 D plus 1, so like a vertex with D plus 1 neighbors that are all leaves, okay, that means that these will be F indistinguishable. That's because by this remark, any graph that has a different number of homomorphisms to these two graphs has to have degree at least D plus 1, right? So it can't be in the family F. It has a maximum degree at least D plus 1. So it can't be in the family F. Right? All right. So great. But that means that this that means in particular that this is not equivalent to isomorphism, right? So these are not isomorphic, right? Because they correspond to these different parity G sub u's, right? And so that means that this is not isomorphism, no matter what D is. All right, so for a D equal to 3, right, you would get these two graphs. So you would take K14 and you get, this is, I think, a K5, but every edge not incident to this vertex is subdivided, and then you have an isolated vertex. And then this is a cube, and then you have some leaves on like these 4 vertices. Okay. Right, basically a max independent set in the cube. So what you see is that, okay, obviously these aren't isomorphic, which we already knew they wouldn't be, but in fact, if counting homomorphisms from graphs with degree at most 3, it doesn't even tell you whether the graph has an isolated vertex or not, because this one has an isolated vertex, but this one doesn't. And in fact, for any D, if you construct this graph K1D, one of them will have an isolated vertex and the other one won't. So for the graphs of some bounded degree, counting homomorphisms from that family, it doesn't tell you whether the graphs even have an isolated vertex or not. Okay, so I have like 1 minute, I guess. So what I want to be true, of course, is that if you have an odd couple for G, then that graph H must have G as a minor. I would love to prove that. I don't have any idea how to prove it. It doesn't seem like it has anything to do with minors, but I haven't found a Cantor example yet. Not that I'm particularly good at that. I'm constructing random things in Sage and checking. But if it were true, then it would answer these questions 1 and 2 affirmatively, which I would also really like to do. And yeah, I think that's nice. Okay, and then I'll just leave this up as the last thing. Okay, thank you.
That's it for a nice talk. So any questions?
Yeah, I have a question.
Yeah.
Hey, Dave. So
Hey.
the original theorem of Lovász, it also is true if you reverse the order of F and G. So if you count the number of homomorphisms from G to F, and it's equal to the number of homomorphisms from H to F for every F, then H and G are still isomorphic. So are some of your classes, do they also work if you reverse the orders?
I haven't really thought much about this other sort of like reversing the order. I know there's been at least one paper that's come out that's looked at sort of these homomorphism indistinguishability, but for the sort of reversed order.
Right.
I forget one of the authors is Albert Atzerius, I believe. I think. But I haven't even read that paper in detail. I've only scanned it. They prove some things, but I don't remember what they are exactly. So I
don't coincide with.
Okay. I mean, like you can get things like, you know, chromatic polynomial by counting homomorphisms on the right. Right? You're counting homomorphisms to complete graphs on the right. That gives you the chromatic polynomial and stuff like this. And I think they prove something like, oh, you can't. I think they prove like, oh, you can't get like you can't get something equivalent to being like having the same chromatic numbers by counting homomorphisms on the left or something like that. But maybe it was a different type of thing that they proved, but something along those lines. So like one of the things you get from the counting homomorphisms on the right, you can't get from counting homomorphisms on the left. I think it was the thing with chromatic polynomial, but I don't remember exactly.
Cool.
Questions? Dave, I also have a question. For the so you said that if it's not homomorphism, I mean if it's not homomorphism under the graph F, then it equivalent to something. So what's that something?
Okay, that's basically
yeah.
that's this theorem, right? So this holds if and only if the something is this. Okay?
Oh, okay. Couple. Okay, so if there's no other questions, let's thank Dave again for a nice talk. And we will be